A subtle rise beneath one of the most closely monitored landscapes on Earth is once again drawing attention to the dynamic processes unfolding far below the surface of Yellowstone National Park. How much movement is enough to matter when the change measures only a few millimeters at a time? What does it mean when an entire region spanning tens of kilometers shifts upward without any visible disruption on the ground? And how do scientists distinguish between routine geological behavior and early signs of something more significant? New satellite observations collected across the year 2025 have confirmed a small but measurable uplift centered near the Norris Geyser Basin, one of the most thermally active areas within the Yellowstone system. The vertical movement, recorded at roughly 1 to 2 centimeters, equivalent to about 0.4 to 0.8 inches, extends across an area nearly 30 kilometers wide or approximately 18.6 miles. While the scale of this deformation might appear dramatic when described spatially, the physical change itself remains extremely subtle, far below what the human eye could detect without specialized instruments. The data comes from a combination of satellite radar interferometry and ground-based positioning systems, both of which are capable of measuring shifts in elevation with remarkable precision. These tools track minute changes over time, allowing scientists to observe patterns that would otherwise remain invisible. In this case, the measurements indicate a gradual and uniform rise rather than a sudden or localized displacement, a distinction that plays a critical role in interpreting what is happening beneath the surface. The Norris Geyser Basin has long been recognized as a focal point for such activity. Known for its high temperatures and complex hydrothermal features, the region sits above a portion of Yellowstone's subsurface system that is particularly sensitive to changes in pressure and fluid movement. The uplift detected in 2025 aligns with what researchers have historically referred to as the Norris uplift anomaly, a recurring pattern in which the ground alternately rises and falls over extended periods. Records dating back several decades reveal that this behavior is not new. Instead, it reflects a broader cycle of deformation that has been observed throughout much of the 20th and early 21st centuries. During certain intervals, the ground surface slowly inflates only to later subside as pressure is released. These cycles can span years or even decades, and their timing does not follow a simple or predictable schedule. What remains consistent, however, is the underlying mechanism driving these changes. Beneath Yellowstone lies a vast and complex system composed of partially molten rock, solidified material, and a network of fluids and gases. The magma reservoir itself is not a single large chamber filled with liquid magma, but rather a heterogeneous mixture in which only a small fraction exists in a molten state. This distinction is crucial, as it influences how pressure builds and dissipates over time. When new magma or hot fluids enter parts of this system, they can increase pressure, gently pushing the overlying ground upward. Conversely, when fluids migrate away or gases escape, the surface may gradually sink back down. The uplift observed near Norris appears to be linked to such processes. Scientists analyzing the data suggest that a combination of fresh magma intrusion and shifting hydrothermal fluids is responsible for the measured rise. The process can be likened to a slow inflation, where the ground responds elastically to changes occurring several kilometers below or a few miles beneath the surface. Despite the analogy, the magnitude of the current uplift remains modest, especially when compared to deformation levels associated with more active volcanic systems elsewhere in the world. Importantly, the spatial extent of the uplift provides additional context. Covering an area approximately 30 kilometers in diameter, the deformation is broad and diffuse rather than sharply concentrated. This pattern typically indicates a distributed source of pressure rather than a single point of intense activity. In practical terms, it suggests that the movement is being driven by widespread processes within the subsurface rather than a focused intrusion moving rapidly toward the surface. Monitoring efforts at Yellowstone rely on a network of instruments designed to capture multiple indicators of activity. These include seismic sensors that detect earthquakes, instruments measuring ground deformation, and systems tracking changes in gas emissions and hydrothermal behavior. Together, these tools provide a comprehensive picture of the park's geological state. In the case of the current uplift, other key signals remain within expected ranges. Seismic activity, for example, has not shown any significant deviation from background levels. Small earthquakes continue to occur, as they regularly do in the region, but their frequency and magnitude do not indicate heightened unrest. Similarly, observations of geysers, hot springs, and fumaroles have not revealed unusual patterns. The behavior of these features remains consistent with long-term trends, without sudden increases in temperature, discharge, or frequency. Another critical factor is the rate of change. While the total uplift measures up to 2 centimeters, the speed at which this change has occurred is relatively slow. There is no evidence of rapid acceleration, which would be a more concerning indicator in volcanic regions. Instead, the deformation appears steady and gradual, aligning with the cyclic behavior documented in previous decades. Historical comparisons further reinforce this interpretation. Past episodes of uplift and subsidence at Yellowstone have often involved similar or even larger magnitudes of change without leading to eruptive events. In some cases, the ground has risen several centimeters over comparable areas before eventually stabilizing or reversing direction. These precedents help establish a baseline against which current observations can be evaluated. The role of hydrothermal systems in this context cannot be overlooked. Yellowstone's surface features are driven by hot water and steam circulating through fractures in the rock. Changes in the distribution or pressure of these fluids can influence ground deformation independently of magma movement. For instance, an increase in subsurface thermal fluids may expand pore spaces and exert upward force on the surface. Conversely, drainage or cooling can lead to contraction and subsidence. In the Norris-Geyser Basin, where temperatures are among the highest in the park, such interactions are particularly pronounced. The area's dynamic nature makes it a key site for observing how hydrothermal and magmatic processes intersect. The current uplift likely reflects a combination of these influences rather than a single dominant cause, underscoring the complexity of the system. Satellite technology has played a central role in capturing these developments. By comparing radar images taken at different times, scientists can detect changes in the ground's elevation with centimeter-level accuracy. This method, known as interferometric synthetic aperture radar, allows for continuous monitoring across large areas without the need for physical presence on the ground. When combined with data from global positioning systems, it provides a robust framework for analyzing deformation patterns. The integration of these data sets has revealed not only the extent of the uplift, but also its temporal evolution. Early signs of the current phase began to emerge gradually, with small increments accumulating over months rather than appearing abruptly. This steady progression is consistent with pressure changes occurring at depth, where processes tend to unfold over longer timescales compared to surface phenomena. Despite the attention drawn by descriptions comparing the affected area to the size of a major city, the reality remains that the physical change is minimal in practical terms. A rise of 1 to 2 centimeters spread over 30 kilometers does not translate into visible alterations in the landscape. Trails, roads, and natural features remain unchanged to the naked eye, and visitors to the park would not perceive any difference without specialized equipment. The distinction between scale and intensity is central to understanding why such events are monitored closely, yet not considered alarming. Large spatial coverage does not necessarily imply significant risk if the magnitude and rate of change remain low. In Yellowstone's case, both factors currently fall within the range of normal variability observed over the past century. As monitoring continues, scientists will track whether the uplift persists, stabilizes, or transitions into a phase of subsidence. Each outcome would provide additional insight into the ongoing dynamics beneath the surface. For now, the data presents a consistent picture of a system behaving in line with its established patterns, where gradual deformation reflects the natural interplay of magma, fluids, and geological structures deep below one of the world's most studied volcanic regions. As the subtle uplift near the Norris Geyser Basin continues to be tracked across 2025, attention remains fixed not on the size of the movement alone, but on how it evolves over time. Patterns of ground deformation within Yellowstone National Park are rarely defined by a single measurement. Instead, they are interpreted through sequences of data points collected over months and years, where consistency, acceleration, or reversal each carry distinct implications. The current phase of uplift, measuring roughly 1 to 2 centimeters, or about 0.4 to 0.8 inches, has developed gradually across a span of several months. This slow progression is a key factor in how the activity is understood. In volcanic systems, rapid deformation over a short interval can indicate a more concentrated and forceful process occurring at depth. By contrast, gradual changes often reflect steady adjustments in subsurface pressure, where material is moving or accumulating without generating abrupt stress within the surrounding rock. Satellite datasets reveal that the uplift is not uniform in every direction, though it remains broadly distributed across an area close to 30 kilometers in diameter, equivalent to about 18.6 miles. Minor variations in elevation change across this region provide clues about the geometry of the source beneath the surface. In many cases, such patterns can be modeled to estimate the depth and volume of the process driving the deformation. While precise values depend on the assumptions used in each model, the general interpretation remains consistent with a source located several kilometers underground or a few miles below the ground. This depth range aligns with the known structure of Yellowstone's magmatic and hydrothermal systems. Beneath the park lies a layered environment where heat, fluids, and partially molten rock interact in complex ways. The upper portion is dominated by hydrothermal circulation, where water heated by underlying magma rises, cools, and recirculates through fractures. Below this zone, deeper reservoirs contain a mixture of solidified rock and pockets of melt, with gases dissolved under high pressure. The interaction between these layers plays a central role in producing surface deformation. When magma at depth releases gases or transfers heat upward, it can alter the pressure conditions within the hydrothermal system. Fluids may expand, migrate, or accumulate in new areas, exerting force on the surrounding rock. Even small shifts in these parameters can translate into measurable changes at the surface, especially when observed across a large area. In the case of the Norris uplift, the current data suggests that both magmatic input and hydrothermal changes are contributing factors. Fresh injections of hot material do not necessarily mean large volumes of molten rock are moving toward the surface. Instead, they may represent incremental additions that increase pressure within already existing reservoirs. At the same time, gases such as carbon dioxide and water vapor can separate from magma and move independently, further influencing subsurface conditions. Gas movement is particularly important because it can occur without generating significant seismic signals. While earthquakes often accompany the fracturing of rock or the movement of magma, the migration of gases and fluids through existing pathways may proceed quietly. This helps explain why seismic activity in Yellowstone remains within typical background levels despite the ongoing uplift. The absence of increased earthquake frequency or magnitude supports the interpretation that the current deformation is not being driven by rapid or forceful intrusion. Another line of evidence comes from the stability of surface hydrothermal features. The Norris Geyser Basin is known for its variability, with geysers and hot springs that can change behavior over time. However, during the period of observed uplift, There have been no widespread or unusual shifts in eruption patterns, water temperatures, or discharge rates. Individual features may fluctuate as they normally do, but there is no coordinated change that would indicate a system-wide disturbance. Temperature measurements collected from thermal areas also remain within expected ranges. If a significant new source of heat were rising quickly toward the surface, it might produce noticeable increases in surface temperature or alter the chemical composition of gases emitted from vents. Such changes are not being observed at a scale that would suggest an escalation in activity. Ground-based instruments provide an additional layer of confirmation. Global positioning system stations installed throughout Yellowstone continuously record their position with high precision. These stations detect the same gradual uplift identified by satellite data, reinforcing the reliability of the measurements. Because these instruments operate independently of satellite systems, their agreement strengthens confidence in the overall interpretation. The concept of cyclical deformation, often described as a form of natural oscillation, remains central to understanding Yellowstone's behavior. Over the past century, records show multiple episodes in which the ground has risen and fallen in response to shifting subsurface conditions. Some of these cycles have involved larger total changes than those observed in 2025, yet none have led directly to eruptive events. This historical context is critical when evaluating current data. Without it, even small changes might appear more significant than they truly are. By comparing present measurements with long-term records, scientists can distinguish between ordinary fluctuations and deviations that warrant closer scrutiny. In this case, the magnitude, rate, and accompanying signals all align with patterns that have been observed many times before. The composition of Yellowstone's magma reservoir further supports this assessment. Studies indicate that the majority of the material beneath the park exists as solid or partially solid rock, with only a limited fraction in a molten state. This structure limits the speed at which magma can move and reduces the likelihood of rapid, large-scale changes. Any new additions of magma tend to be absorbed into this framework, contributing to pressure changes rather than immediate surface activity. It is also important to consider the role of structural features within the crust. Faults, fractures, and existing pathways created by past activity can influence how pressure is distributed. In some cases, these features allow fluids and gases to move laterally, spreading the effect of pressure changes over a wider area. This can produce the type of broad, low-amplitude uplift currently being observed near Norris. Monitoring efforts are designed to detect not only the presence of deformation, but also changes in its nature. A shift from gradual to rapid uplift, an increase in earthquake activity, or significant alterations in hydrothermal behavior would each represent a different set of conditions. The absence of these indicators at present reinforces the interpretation that the system remains within its typical range of variability. The terminology used to describe such events can sometimes create confusion. Words like uplift and inflation may suggest dramatic movement, but in geological terms they often refer to changes that are only measurable with specialized equipment. In Yellowstone's case, the current uplift is best understood as a minor adjustment rather than a large-scale transformation. As data continues to accumulate, scientists will refine their models to better understand the underlying processes. Each new measurement contributes to a more detailed picture of how Yellowstone's subsurface system operates. Over time, these insights improve the ability to interpret future changes, providing a clearer distinction between normal behavior and conditions that might signal a departure from established patterns. For now, the situation remains consistent with a system that is active but stable. The ground beneath Yellowstone continues to respond to the natural interplay of heat, pressure, and fluid movement, producing subtle changes that are detectable only through precise observation. The current uplift near the Norris Geyser Basin fits within this framework, representing another phase in a long sequence of natural cycles that have defined the region for generations. And while the numbers themselves may seem small, The ability to detect and understand such minute changes reflects the sophistication of modern monitoring technology. It is through these tools that even the slightest movement can be recorded, analyzed, and placed within the broader context of Yellowstone's ongoing geological activity. If you found this breakdown clear and informative, make sure to like, share, and subscribe for more updates like this. And do not forget to tap that hype icon to help this video reach a wider audience.